Hey, what's up there, sixth grade? I just wanted to post a little kind of a YouTube clip for you guys so you can go through. This is obviously how our typical lecture would go. Obviously, the big difference is being that I don't have you guys to interact with, but this is just something as a resource for you if you feel like you're struggling, something to maybe even solidify some of the information that maybe you've gone over already. So this is going to, as I told you last week, we're starting to get into the atmosphere. We're going to start getting into weather as well, and so we're moving away from some of that geology that we covered earlier this year. But obviously, don't forget it because a lot of what we learned with that geology is going to be applied here to even some of the weather and a lot of the way the atmosphere has been able to form for us. So in this section, okay, we're going to be talking about why the atmosphere is important, how it formed, and what is keeping it in place. Okay, so there's a lot of different reasons why the atmosphere is important, but just to streamline some of those, okay, so the atmosphere is a thin layer of gases surrounding Earth. It's hundreds of kilometers high. Earth's atmosphere contains a layer of insulation that helps keep temperatures on Earth within a normal range, right? So this is what prevents, we've talked about sometimes on other planets, what you end up having happen is, you look at something, a planet like Mercury, or even talk about going to, Earth's own satellite here, our natural satellite, the Moon. You know, the the temperatures have such extreme opposites, right? It's hundreds of degrees difference between being in that direct sunlight and now being cast in the dark side of the moon or the dark side, at that nighttime for that planet. Because of Earth's atmosphere, we end up kind of never, staying in what they refer to as a Goldilocks zone, and that's what makes Earth so unique, right? We don't have, unlike a lot of the other planets in our solar system, and what we assume too is a lot of planets, even that we found circulating other stars in other solar systems. We're in a really unique range where we have a stable climate, stable atmosphere. Our gaseous compounds don't really fluctuate too severely, which allows life to kind of thrive here. So that's why they kind of call it that Goldilocks zone. It's not too close to the sun where it's too hot. It's not too far away where it's going to be too cold either. Although we are finding now that there are some planets that are able to kind of break that a little bit, or at least break that range of what we thought was previously possible. So that's kind of something that's always developing and always changing. So another thing here, so it's protecting from the harmful rays. So this is going to reflect a lot of the sun's UV rays back. If we were getting bombarded with those constantly, cancer rates are already pretty high, but they would be even higher. Life on the surface of the Earth would likely not be possible without the help of the atmosphere. All right, and friction within the atmosphere causes most meteorites to burn up before striking Earth. I have a couple of videos that I'm going to show you. This is going to be a pretty crucial one. We've seen what we haven't really talked about it in too great a detail, but a lot of Earth's mass extinctions or mass die-offs have been a result of an atmosphere. A meteorite that's actually penetrated our atmosphere, and when it makes contact, sends a lot of debris into the upper atmosphere, and that ends up getting into the jet streams, and then it circulates around the atmosphere and ends up blocking out the sunlight. That kills off a lot of the primary producers. Those producers get cut off. Everything else above it eventually has a knock-on effect. All right, so this is just depicting, you've probably seen images of this from the International Space Station. It's really cool to be able to see, not just straight down, but even as you look off, right, you could see the layers of the atmosphere as it reaches the curvature of Earth. Yeah, Earth has a curve to it. It is not flat, as much as you guys like to troll and talk about that. It does have a natural curvature to it. It's and look at other planets, right? Other planets are spherical. Why would we be the only one that is flat, right? Would kind of defy the laws of physics. I want you guys to write this section down. So it's this acronym PAPOW. So this is just streamlining the information of what makes the atmosphere so important. So it's going to protect us from those UV rays. It's going to protect us from meteors. It's going to provide oxygen. I know that that's another P, but whatever. Oxygen is being provided to living things. It's going to keep us warm, and it's going to be a source of water. So protect from UV, protect from meteorites, oxygen's being provided, warmth, and water. All right, those are the 5 key things associated with our atmosphere. Right? The other thing that happens, right? We have this greenhouse effect. Now we're at a point where it's not necessarily as problematic as what you would see with a planet like Venus, right? Venus is the hottest planet in the solar system, even though it's the second closest to the sun. So it's even hotter than Mercury, which is the closest to the sun. And the reason for that is the greenhouse gases, right? The greenhouse gas effect that happens there. As UV light gets trapped inside the atmosphere, it kind of ends up bouncing back and forth and staying inside there, almost like a common comparison is a car on a hot day. So if you've seen like a car in the summer, light is able to penetrate those windows and come in, but the heat itself does not radiate out as much because it's kind of trapped inside the vehicle for the most part. Similar idea here. All right, this is just showing. This was in Russia, and I think it was 2013. So it was about 7 years ago. There was a meteorite that actually came through. You could see, with meteorites, they typically follow this path, which means like it's not coming straight down, right? It ends up arcing into the atmosphere, and that's usually the best trajectory that we could have because as it's traveling through, it hits different layers of the atmosphere. And each of those different layers of atmosphere, as it increases air resistance, it's going to increase that friction. And as there's more friction, there's going to be more heat, which means this is going to burn up and break apart more and more as it gets closer to Earth's surface. I want to say that this exploded, I thought it was something like 10,000 feet above Earth's surface. So this did not come in contact directly. Obviously, the debris falling, the meteor itself broke apart before it hit Earth's surface, but the primary explosion took place above Earth's surface. And that's kind of what you see. That's kind of what you see in this end phase right here, as it's entering Earth's atmosphere. And that's why we even talk about, like, to put it in perspective, a lot of the shooting stars that you see at night, a lot of those are about like the size of a grain of sand or so entering the atmosphere, and it's just such an intense amount of heat and that contrast of light that allows you to see it. There's if it's your likelihood of seeing shooting stars on a new moon, so there's even less lighting, less natural light, as well as less artificial light if you can get away from street lights. Your likelihood of seeing shooting stars goes up tremendously. Whereas if it's happening, shooting stars are reaching Earth's surface during the day, but the power of, the intensity of the sun's light is kind of restricting you from being able to see it. All right, I think that's just a video you guys can kind of thumb through and watch if you want to see what happened if you want to see what happened in Russia. All right, so this is kind of the origins of Earth's atmosphere. So a lot of it came from a lot of that volcanic activity that was taking place in early Earth. Um, it caused a lot of gases to escape, and the reason it doesn't get sucked off into the vacuum of space is because Earth has a tremendous amount of gravity that's able to keep those gases from filtering off into space, right? So it keeps everything condensed. Now, that being said, as you continue going up in elevation and altitude, the air is getting thinner, right? So it thins out until you obviously reach what is outer space, right? Where you do still have some gases, but it's not enough where if you were out of a spacesuit or anything like that, that you would be able to breathe without, at least for an extended period of time, especially depending on the location of the sun in that moment. All right. Again, this is just like kind of a depiction. All the different gases, a lot of the CO2 being a big one that's emitted. We've seen volcanic eruptions in the last chapter, and those plumes of smoke. It's adding a lot of different chemicals to the atmosphere. An excessive amount of it is obviously going to be detrimental, but if it didn't exist or if it didn't happen, our atmosphere would not be what it is today. So it's definitely, in some cases could be destructive, but long term and for long term life on Earth, it's essential. All right. So as the atmosphere cooled, water vapor condensed into liquid that fell as rain. Over thousands of years, the rain formed Earth's oceans. Carbon dioxide from the atmosphere dissolved in rainwater and fell into the oceans. Organisms that use photosynthesis produced the oxygen in today's atmosphere. This is something you're going to see and get into greater detail on in 7th grade, but a lot of the early life was aquatic. You had a lot of photosynthetic algae that formed the first producers for early Earth. But this would have never been able to happen without these steps prior to that, right? So it was the release of those volcanic gases, and even through like releases of like asteroid impacts, releasing gases that get trapped in some of the layers of Earth. So those were contributing to Earth's early atmosphere. All right, this is just showing like a CO2 cycle. So if you remember last year, right, photosynthesis is a crucial part of establishing life on Earth, taking in CO2, giving off oxygen that animals are able to, or really any aerobic organism is able to go through. We do have humans contributing with carbon emissions as well, but you could see how the introduction of CO2 is what's also contributing to some of the cloud cover that you see in the atmosphere as well. All right, so contrary to popular belief or what you might assume would be the case with the atmosphere, nitrogen makes up the bulk of our atmosphere. So this makes up almost 80% of the atmosphere, and oxygen makes up almost 20%. So between these two, they make up about 99% of the atmosphere. A lot of people assume humans need oxygen. A lot of the life on Earth needs oxygen. It has to be made up of mostly oxygen. Well, that is not the case. And it's actually really good that it's not the case. If it was any higher than 21%, if it was, let's just say if these numbers were reversed, right? If it was 70 or 80% oxygen, we would have a huge issue. We would have a really big issue with wildfires, right? That would be among many other problems as well. But especially with plants not being able to go through photosynthesis properly. But taking that out of effect, looking at something like this past year with Australia and the Australian wildfires, California wildfires last year, if we had a higher concentration of oxygen in the atmosphere, those fires would not be, not only would they not really be stopped, they wouldn't be able to slow down at the rate that they do now, right? As we know, oxygen fuels fire, so as it continues to, it would basically burn uncontrollably and at higher heats and higher intensities. So it's a huge advantage that we have just the right amount of oxygen in our atmosphere where we're able to breathe and thrive, but it also doesn't allow wildfires, which are naturally occurring, to proliferate too much. All right. So again, we mentioned this before. Volcanoes are sending solid particles and liquid acids into the atmosphere. All right. So we do have, and you see in this next little pie chart here, they call it air soup, and it just is showing that the air that we breathe isn't, you're not breathing in, as you see, it's not pure oxygen, it's not pure nitrogen, right? It's going to be a compound, it's going to be combinations of a lot of different elements, right? Xenon being another one, neon, hydrogen, helium, krypton, carbon dioxide, right? There's trace amounts of other gases in the atmosphere, with carbon dioxide coming in at in a third place there. All right. So the atmospheric layer closest to Earth is the troposphere. The warmest part of the troposphere is near Earth's surface. So I'm going to just jump to this slide for one split second and then go back. As you go up in altitude, it gets colder. So the higher you go, the colder it's getting, right? Heat is rising. So it's the next level, it's the next layers above the troposphere that start to actually warm up. But in this case, from Earth's surface up, it starts to actually get colder as you go higher in altitude. All right? The stratosphere is the atmospheric layer directly above the troposphere. The area of the stratosphere that has the greatest amount of ozone gas is the ozone layer. So that's what's showing you. So again, just to give you like a little reference, right? Above some of the highest clouds, that 5 to 8 miles high, as you go up, it's decreasing in temperature. As soon as you hit above that ozone layer, right, starting to meet some of that ozone layer, it begins to increase in temperature. And that if you've heard as well over reading any scientific articles, or maybe you've even heard it on the news about problems with Earth's ozone layer. If we have a hole in Earth's ozone layer, it is incredibly problematic. You would, the areas that it does have it, you're exposed to greater amounts of UV light. It's contributing to global warming in some pockets. If you have a hole in the ozone in an area over the ice sheets, for instance, you could be having huge issues with polar caps melting as well. But and a big part of the problem with this was they were actually finding this was something back in the 80s. You had what was known as CFCs, chlorofluorocarbons, and that was it was in some aerosols. It was in so it could be like different types of like spray paints or hairsprays. But when those CFCs interacted with the ozone, it started to break apart and destroy the ozone. And destroyed the ozone, to a point where the scientists actually thought it wasn't able to recover. Fortunately, after removing those CFCs, it has been able to recover. It wasn't only the ozone layer that was impacted by those CFCs. A lot of animals were also impacted as well, namely some bigger birds of prey, like I know the peregrine falcon was a big one. If you maybe you've heard that, that's like the fastest diving falcon. It died at like 200 miles an hour. But what was happening with them is these CFCs, when it was kind of interacting with them during when they lay eggs, the egg shells were actually kind of too thin from those CFCs. So it was a huge issue. But again, that was something they learned from. They removed it, and things are trending in the right direction now. All right. So UV rays, which can kill plants and animals, are absorbed more effectively by ozone than oxygen gas. So this is the portion of the environment that, when we're saying protect, so that in that PAPAL, so hitting that first P, protecting us from UV light, that's what this ozone is responsible for. Again, the only reason life is able to exist on the surface of Earth is because of this. Without that, we'd be getting bombarded with radiation. So life wouldn't be able to exist. And that's not just human life, that's any terrestrial life. All right, so combined with the mesosphere and the thermosphere are layers of the atmosphere that are much broader than the troposphere and the stratosphere. They have a low density of gases. The ionosphere is a region within the mesosphere and troposphere that contains ions. Displays of colored lights called auroras occur here. So if you've ever seen, I know Patrick Knight, you've been to Iceland. I know a big, a cool event that you can see there is seeing the auroras. In the northern hemisphere, we see the aurora borealis, where in the southern hemisphere you can see the aurora australis over Antarctica. But you have Earth's light. In some cases, you have these like solar flares that end up interacting with our electromagnetic sphere, and it gets concentrated over the poles. And when that happens, you kind of have this exchange of lights and ions, and that's what's giving off these. It's giving off these colored lights that we're able to see. And then you have the outermost layer, right? That exosphere is gas molecules, where they're mostly dispersed to points where they really aren't even interacting with each other. They're not even coming in contact. This is where it might be diffusing off into space, or possibly kind of falling back down to a different layer, depending on what may have occurred. All right, so this is just showing again, another one of these depictions of what happens at each of the layers. I know it's in kilometers, but you can see what's common. This is that Russian video we were watching, right? So in this layer here, this is where you have the most meteors able to be burning up. Rockets are able to kind of reach, like these would be more so those like ICBMs, those intercontinental ballistic missiles. And then above that, in this is our exosphere here, and even the upper portion of the ionosphere. Again, that's going to be where we're just in that sweet spot of not necessarily getting, you're still getting pulled back in towards the atmosphere, but it's requiring less energy to keep yourself from getting pulled into it, right? We're not at terminal velocity where we've escaped Earth's atmosphere. If I said atmosphere, I meant to say gravitational pull. But we haven't escaped Earth's gravitational pull, but we don't have to work quite as hard to keep our distance from Earth. Okay, showing the International Space Station. All right. Now, this was just posing the question, why you think the exosphere, and if you look here in this diagram, you're going to see some diagrams are going to vary quite a bit. This is saying 700 kilometers is how far out the exosphere is able to go, and maybe even further than that. And that's because, depending on what model you're looking at, the way they're calculating the distance that gas is able to escape and go is going to determine how far out the exosphere is able to go. So, while this model might be saying 300 kilometers, this one is going to be showing. This one's going to be showing even greater distance as well. And that's kind of the case with a lot of different models as well. But what matters is that they're showing or talking about how the exosphere, that's where you have those dispersed gaseous particles. All right, as we're getting at the end here, so air pressure and altitude. So gravity pulls gas particles in the atmosphere toward Earth's surface. As I said before, this is what is preventing it from flying off into space. Air pressure is greatest near Earth's surface because all the molecules of the atmosphere push downward on the lowest layer of air. You could almost compare this, and I think it was in that Bill Nye video that we watched as well. You could almost compare us to like lobsters on the seafloor, right? But instead of it being, thousands of pounds of pressure from Earth's oceans, right? We're under a much more bearable amount of pressure with just the gaseous particles. And this is actually also why helicopters aren't able to work at higher altitudes. The best way to kind of compare it is helicopters are similar to how you would almost swim. Think about how you might propel yourself with your hands with a downward force to propel yourself up. Obviously, you can't do that in air, right? It's too thin, but it's when you hit a material that gives enough resistance that allows you to have an upward force and is allowing you to move through it. Now, with like a helicopter, right, that propeller spinning, it's creating a downdraft, right? It's creating, it's pushing off of the particles underneath it. And that's why helicopters are not able to go higher than a plane. This is also why if somebody needs an emergency rescue, say on Mount Everest, right? Helicopters, not only would the turbulence be really bad up at that altitude, but even if it was perfect conditions, it's not able to, there's not enough particles for it to push off of, to kind of hover. What ends up happening is it ends up kind of rising, and then it gets to a point where the propeller's still spinning, but it's going down until it hits a layer that it's able to push off of, right? So it does have a maximum height that it's able to kind of reach. But a big part of the reason for that, lower pressure as you go higher, higher pressure as you go into a lower altitude. Closer to Earth's surface, it's where you have the most concentrated air particles sitting on top of you. All right. We could go through, we'll go through the two main ones. So why is the atmosphere important? You can go back to the beginning of the video and talk about PPOW, right? It's that idea of protecting from protecting from the sun's UV rays, protecting from meteorites. Oxygen is being provided, water is being provided, and warmth. It's that blanket of warmth. So the atmosphere is what allows really all life to exist, right? Even aquatic life. Everything is relying on the atmosphere to be there, right? We see how many other planets in our solar system don't have an atmosphere or don't have an atmosphere like ours, and life isn't able to exist, best we know, on any of those. All right, so which kinds of organisms were important in the evolution of the atmosphere? This goes back to the introduction of algae and those first photosynthetic organisms. They're the reason we have any oxygen in our atmosphere. Okay, so this was just a quick little half-hour video for you guys. If you have any questions, any concerns, reach out to me. This is just supposed to be some supplementary material for you. Hopefully you guys are getting through this e-learning all right. But as I said, reach out to me if you're having any issues. All right? 6th grade, keep it up. I'll talk to you soon.